Okay, we're going to talk about the mechanical advantage of tire irons. And I had the unfortunate discovery that my tire iron was not in my trunk. So this morning I bought another tire iron. This is a bright, shiny new one. And I asked the folks at the hardware store if they would get me one single lug nut that I have brought, just so I can show the mechanical advantage of what a tire iron does without having to take the lug nut off my car's tire. So here's the lug nut and how it would normally fit in there. And if you look closely, the lug nut is not a tight fit to the socket it's supposed to fit in. And that'll come into play when we talk about the mechanical advantage there. And of course, this tire iron has various sizes, and so it becomes a useful tool with various size lug nuts. But for me, my lug nut size is a 22 millimeters. So we're going to use metric units for this. And some of the measurements I have to take will be the length of this part that contains the lug nut that I'm wanting to twist. This is the part of the tire iron that I'm going to twist. This arm is going to take torsion, this part. And I just dropped my lug nut. Okay, so when I go to use this tire iron, I'm going to want to twist this part in order to turn the lug nut, which means the two perpendicular arms, this one and this one, are going to take a force up and down. Now if I'm going to tighten this, it's going to be, for me, a clockwise turn, a righty-tighty, right? Okay. So that means with my right hand I'm going to push down, with my left hand I'm going to pull up, and that will tighten the lug nut. If I want to loosen it, it's the other direction around. So on the tire it would look like this. Okay, so the way this works is if I'm going to loosen this, I push down on this side and I pull up on this side. So the force looks a little bit like this. Got an upward force on this end, a downward force on this end, and that force transmits a bending moment through to this end, and this part becomes a cantilever beam, and this force transmits a bending force to this point, and this part becomes a cantilever beam. And so the bending moment from here and the bending moment from there, they both contribute to a twisting motion that has to transmit that torsion, that twisting, through the axis of this bar. And that has to happen through the weld that connects these two cross bars. And that transmits through a force called shear. And we're not going to talk about shear yet, but just trust me that the force that we have in twist is going to transmit through this axis as a twisting motion. Another word for twisting motion is torsion. And then at the end of this, tire iron, this twisting motion, if I'm going to lefty-loosey, right, I'm gonna tighten this. This twisting motion is going to rotate this direction around. So I'm going to, from my perspective, it's going to be counterclockwise. From your perspective, that's going to look, from your side, twisting like this, so that it's going to look clockwise from your side of the camera. Alright, and the result is this thing is going to tighten the nut, like so, right? It'll tighten it. Now, to tighten it, this contact on the inside of the tire iron has to force a contact with the lug nut so that it creates a series of 6 forces on the inside of this hexagonal depression. And those 6 point forces produce 6 point forces on the nut part of this lug nut. And those 6 point forces produce 3 force couples. And those force couples we'll talk about mathematically when I get to the next part of our discussion, which will be on paper. We're going to talk about the math of this, of the process of this, okay? So in order to make the tire iron work, I've got to have enough force to crank through this tire iron to make the twist happen in order to loosen the lug. If not, well, then we have a problem and the lug does not come off. And same thing, if I don't have enough strength to tighten it to put this back on properly, well, then I could lose my tire somewhere down the road. All right, so let's move on to the math.